Right now, as you watch this, your brain is undergoing structural changes at the molecular level. Every experience, every thought, and every action triggers a cascade of neural activity that physically reshapes your brain, a phenomenon known as neuroplasticity. But how does this actually happen on a cellular level? Let's break it down. At the core of neuroplasticity is synaptic plasticity, the ability of synapses, the junctions between neurons, to strengthen or weaken over time. This occurs primarily through two well-studied processes: long-term potentiation, or LTP, and long-term depression, or LTD. LTP is the strengthening of synapses in response to repeated activity. When a neuron is repeatedly stimulated, NMDA receptors, a subtype of glutamate receptor, allows calcium ions to flood into the postsynaptic neuron. This triggers a series of intracellular signaling cascades, activating CAMK2, or calcium calmodulin dependent protein kinase 2, and protein kinase A. These kinases phosphorylate AMPA receptors, increasing their presence at the synapse, which enhances the neuron's sensitivity to future signals. Over time, this structural remodeling leads to dendritic spine growth, increasing synaptic connectivity and strengthening neural circuits involved in learning and memory. On the other hand, LTD occurs when synaptic connections weaken due to low-frequency stimulation. In this case, low intracellular calcium concentrations activate protein phosphatases instead of kinases, leading to the internalization of AMPA receptors. This process fine-tunes neural circuits by eliminating redundant or weak connections, preventing excessive noise in neural communication. Beyond synaptic changes, neuroplasticity also involves neurogenesis, the birth of new neurons, particularly in the dentate gyrus of the hippocampus. This process is driven by brain-derived neurotrophic factor, or BDNF, a key protein that promotes neuronal survival, growth, and synaptic remodeling. Exercise, enriched activities, and learning activities all upregulate BDNF, enhancing cognitive function and emotional resilience. Neuroplasticity is also key for recovery after brain injury. If a region of the brain is damaged, intact areas can compensate by forming new synaptic connections, a process known as cortical remapping. After a stroke, for example, surviving neurons increase the expression of immediate early genes like CFOS and ARC, which help establish new neural pathways to restore lost functions. Even in cases of extreme brain damage, such as hemispherectomy, where an entire hemisphere is removed, the remaining brain tissue can reallocate functions through large-scale plasticity. But neuroplasticity isn't always beneficial. Maladaptive plasticity occurs in conditions like chronic pain, addiction, and PTSD, where neural circuits reinforce harmful behaviors or persistent pain states. In addiction, for example, repeated drug exposure hijacks the brain's dopaminergic reward system, reinforcing compulsive drug-seeking behaviors through excessive synaptic strengthening in the nucleus accumbens. So, whether you're learning a new skill, recovering from an injury, or rewiring bad habits, your brain is constantly reshaping itself. And the key to harnessing neuroplasticity is to stimulate learning, engage in complex activities, and challenge your brain regularly. Because every good experience, or bad, literally rewires who you are.